All right, folks, here we are continuing in Chapter 10 and Section 10.5. We're going to look at two comparison tests. The first one's called a direct comparison test, and the second one's called a limit comparison test. So far, we've looked at series that have positive terms. And our toolbox contains so far, we've looked at telescoping series, geometric series, the nth term test for divergence, the integral test, and the p-series test. So in the future here, we may encounter series that looks geometric, or it looks like a p-series, or it even looks like a candidate for the integral test, but something is just a little bit off. For example, we know the series 1 over 3 to the n is geometric, but n over 3 to the n is not geometric. We know the series 1 over n squared. We know that's a p-series. But the series 1 over n squared plus 1, that is not a p-series. We know the series n squared over the quantity n cubed plus 2 squared, that's easily integrated. I mean, a basic u substitution would take care of it. But at one little change, making it the series n cubed over the quantity n cubed plus 2 squared, well, that is not easily integrated. But now, due to the similarities to a known series, n over 3 to the n is similar to a geometric series 1 over 3 to the n. 1 over n squared plus 1 is similar to the p-series 1 over n squared. N cubed over n cubed plus 2 squared is similar to n squared over n cubed plus 2 squared. So due to those similarities to a known series, we can attack these similar ones using what is called the direct comparison test. Well, I'd like to say direct comparison test, limit comparison test. These are a couple of my favorite tests. They're actually all my favorite tests. I just think this material is pretty cool. Quick point of clarification. Your book calls the direct comparison test. It just simply calls it the comparison test. You know, I don't like the name comparison test. There's a reason why it should be called the direct comparison test. And for that reason, I am going to call it the direct comparison test, and I'll abbreviate it as DCT. So here it is. Here's your direct comparison test, or DCT. Let 0 be less than or equal to a sub n, less than or equal to b sub n, for some little n bigger than or equal to uppercase n. That's a really important preamble there. Just the part a sub n less than or equal to b sub n. Well, first off, notice since a sub n and b sub n are both greater than or equal to 0, we're dealing with series that will not have any negative terms. So that's the first really important thing about the preamble. The second important thing about the preamble is a sub n is less than or equal to b sub n. Before I go with the rest of the theorem, just think about this for a minute. A sub n is less than or equal to b sub n. If I know the series b sub n converges, doesn't it make sense that something smaller than that, the series a sub n, would also converge? I hope so, because that's the first part of the direct comparison test. If the series b sub n converges, then the series a sub n converges. Logically, that makes sense. If you know the series b sub n converges, something that is smaller than it must also converge. So look at that preamble again. 0 less than or equal to a sub n less than or equal to b sub n. If I know the series a sub n diverges, doesn't it make sense that the series b sub n must also diverge? I mean, it's larger than a sub n. If we know a sub n diverges, something larger than that should also diverge. Hopefully that does make sense because that's part 2 of the direct comparison test. If the series A sub n diverges, then the series B sub n diverges. Series A sub n diverges, then something that's larger than it, the series B sub n, must also diverge. That is the only thing, the only 2 things that the direct comparison test tells us. And it all flows from that preamble. And you'll hear me mention that several times as we do a couple of examples. I've already mentioned this, but I have it as a note. We're still dealing with positive term series. In other words, the direct comparison test can only be applied for positive term series. So let's look at an example. Typical directions, do the following, converge or diverge. And here are 3, A, B, and C. So you know the drill by now. Make sure you have this in your notes. Each one of these series, this is an example. Make sure you have each one in the notes because at this time, I'm going to head off to the chalkboard and work them out. All right, folks, here our first example. We're asked to determine if the following series converge or diverge. In part A, the series was n equals 1 to infinity, 1 over 2n, 1 over 2 to the n plus 1. So the first thing I would say is, boy, that really kind of sort of looks like a geometric series. In fact, I would say that it looks like the geometric series 1 over 2 to the n. And we know that geometric series, 1 over 2 to the n. We know it's a geometric series. So it's a geometric series. R equals 1/2, which is less than 1. So we know this geometric series converges. So here's what I need to do. I will every single time write down that important preamble of the direct comparison test. That preamble which says A sub n is less than or equal to B sub n. Now remember what the direct comparison test says. It only tells you 2 things. Thing 1, if you know this series converges, then you know something that is smaller must also converge. The second thing it tells you, if you know this diverges, then you know something that is larger than that must also diverge. So in order to use the power of the direct comparison test for this problem, I have to have the 1 over 2 to the n for B sub n and 1 over 2 to the n plus 1 for A sub n. Now folks, I can't just write that down and say, hey, everything's good. I have to make sure this inequality is actually true. Now here's an easy way to check that it's actually true. You have a fraction and a fraction. Notice both fractions have the exact same numerator. Also notice this denominator will be a little bit larger than this denominator. When the numerators are the same, the fraction that has the larger denominator is going to be the smaller fraction. Let me think about it. Compare 1/6 to 1/8. Compare 1/6 to 1/12. I mean, the fraction with the larger denominator is the smaller fraction as long as the numerators are the same. So when I look at this, I'm going to say, I know this is true, and I will allow you to say it's true by that denominator argument that I just made. But you better make sure it's true. So now this is where the power of the direct comparison test comes in. You know the series 1 over 2 to the n. You know it converges. That means something that is smaller must also converge. So we conclude that the series 1 over 2 to the n plus 1, it converges thanks to the direct comparison test with the known convergent geometric series 1 over 2 to the n. That's it for part A. Alright, so let's look at part B. Does the series n equals 1 to infinity 1 over 2 square root n minus 1, does it converge or does it diverge? Well, let me just start off by saying this kind of looks like the series 1 over the square root of n, which we know that series is the same thing as 1 over n to the 1/2. What kind of series is that? That's right, it's a p-series. It's a p-series. P is equal to 1/2. That's less than 1. So we know that that series diverges. This series diverges. I'm going to write down another series. If I know the series 1 over square root n diverges because it's a p-series, don't I also know the series 1 over 2 square root n? Don't I know that it also diverges? Yes, I do. I know that diverges because it's simply 1/2 times the divergent 1 over the square root of n. Remember, multiplying a series by a non-zero constant doesn't affect divergence or convergence. You take a divergent series, multiply it by any non-zero number you want, you still have a divergent series. So now I'm ready, because I have something now that looks really close to my original series. I'm ready to write down that preamble for the direct comparison test. The a sub n is less than or equal to b sub n. So for this one, to use the power of the direct comparison test, the 1 over 2 square root n, it has to be in place of a sub n. It has to be in place of a sub n because we know it diverges, and the direct comparison test says, well, if this diverges, something that's larger must also diverge. So this is what the inequality has to look like from the preamble. But remember, I can't just write it down and say, yep, that's good. I have to check, I have to make sure this inequality is true. And I think it is because of the denominator argument. The numerators are the same. This denominator is always larger than that denominator. So it's the same denominator argument that I told you about right here. So I know this is true thanks to the denominator argument. So I can now conclude that the series 1 over 2 square root n minus 1 diverges thanks to the direct comparison test with the divergent series 1 over 2 square root n. There was a part C, so let me erase the board and put part C up here. I didn't think I would have enough room for all three parts initially, so here we go. Let me get part C up here. Let's see, C was the series from n equals 1 to infinity, 1 over n squared plus 1. Alright, this series should look familiar. If you recall, this was an example I did once we learned the integral test, because it was easy to integrate it. But you know, I knew the direct comparison test at that time, and it was all I could do to not use the direct comparison test. Because when I see this series, what immediately jumps out, yeah, it's easy to integrate, but what immediately jumps out to me is that it looks so much like the series 1 over n squared, which we know converges. It's a p-series. P is 2, which is greater than 1. So we know it converges. I write down, and I encourage you to always write down the preamble of the direct comparison test. I mean, the preamble tells you everything you need to know. One more time, you write down the preamble. If this series converges, something that's smaller must also converge. If this series diverges, well, something that's larger must also diverge. That's it. That's all the direct comparison test tells you, but it comes logically just from this preamble. So in order to use the power of the direct comparison test for this problem, since we have a convergent series, we're comparing it to 1 over n squared. 1 over n squared would have to go in for b sub n, and 1 over n squared plus 1 would have to go in for a sub n. But once you write this down, you have to make sure it's true and state a reason for why it's true. So I look at this inequality and I say, is that true or false? Well, it's true. The numerators are the same. This denominator is larger than that denominator, so this fraction will be smaller than that fraction. So I'll say the denominator argument. It's true because of the denominator argument. So that tells me that the series 1 over n squared plus 1 converges thanks to the direct comparison test with the known convergent p-series 1 over n squared. All right, so just to practice this, give you a little bit more practice, I would like you in the book to do number 13 and number 19. So you know the drill by now. Pause the video, do number 13, do number 19. Once you've done them, restart the video. I'll be here at the board working out the solutions. All right, here number 13, you were asked, does the series n equals 1 to infinity, square root n over n squared plus 3, does that series, does it converge or does it diverge? To me, this kind of looks like the series square root n over n squared. It resembles that series, which we know is, well, square root of n, that's n to the 1/2, and the bases are the same, so you'd have n to the 1/2 divided by n squared. When the bases are the same and you're dividing, you subtract the exponent. So 1/2 minus 2, that would be a negative 3/2. So that's 1 over n to the positive 3/2, and we know something about this. We know this is a p-series. P is 3/2, which is greater than 1. And it converges. So I'm going to write down that all-important preamble for the direct comparison test. That's going to be my b sub n, because the power of the direct comparison test, it's like I know this converges, so a series that is smaller, oh, here it is, must also converge. Okay, so I wrote this series here. We know that it converges. But keep in mind, this series was nothing more than simplifying down the square root n over n squared. So I'm going to replace that with square root n over n squared. Do you see why I wanted to do that? These numerators are the same. This denominator is a little bit larger than this denominator. So I know this inequality is true thanks to that denominator argument. So I can now conclude that the series square root n over n squared plus 3 converges thanks to the direct comparison test with the series, and you could write down the series as square root n over n squared, or you could write it down as 1 over n to the 3 halves. It doesn't matter. I would probably do the 1 over n to the 3 halves because I have all this work here, but I would probably write this down because then if someone else is looking at it, they can quickly say, oh yeah, that's a p-series. So that was it for number 13. Number 19. You knew I couldn't resist getting a series in here that involves a trig function. I mean, that's kind of cool. All right, so we're going to begin with this. All right, well, I see a 1 plus cosine squared n over an n minus 3. So I'm looking at that numerator, a 1 plus cosine squared n. So I know for all positive integers, n, I know this is going to be a positive number because anything squared is positive. So what does that tell me? If that's positive, I think it tells me that 1 is less than or equal to 1 plus cosine squared n. I mean, that has to be the case. All right, now what? I could divide both sides. I could divide both sides of that by, I could divide both sides of that inequality by n minus 3. Look what I'd get. I believe I wrote something down wrong. I think in number 19, didn't this n value start at 4? I think it did. I think it started at 4. I don't know why I wrote a 1 there. Okay. You know what I think I just stumbled upon? I think I just stumbled upon A sub n and B sub n for the direct comparison test. So I need to now analyze, what about 1 over n minus 3? What about that series from n equals 4 to infinity? Does it converge or does it diverge? Well, doesn't it look like the series 1 over n, the harmonic series? And if I write down the preamble for the direct comparison test, we know the harmonic series diverges. Is that inequality true? Yeah. It's true by the denominator argument. The numerators are the same. This denominator is always going to be larger than that denominator, so this fraction is always smaller than this fraction. So since you know the harmonic series diverges, you can conclude 1 over n minus 3 diverges via the direct comparison test with the known divergent harmonic series. Then this information is used to tell us that this series diverges thanks to the direct comparison test with this series that we just determined diverged. This was kind of a cool one. I really kind of liked it because, you know, basics of trig allowed us to write this inequality. Basics of algebra allowed us to write this, which then kind of told us Hey, direct comparison test, we know what A sub n and B sub n is, but do we know this series diverges? Do we know that? And I was like, well, let's write it down. It looks like the harmonic series. Let's crank this through a little mini direct comparison test off to the side so we can then employ the power of the direct comparison test on the original one. That was really cool. I like that. So there were 3 examples, 2 homework problems dealing with the direct comparison test. So, hey, let's head back to the slides and see what's next. All right, hopefully after doing that example, all 3 parts and a couple of homework problems, you're starting to get the hang of the direct comparison test and why that preamble is so important. And exactly, if you know the preamble, you know the direct comparison test. Now, often we're going to have a series that resembles a p-series or, say, a geometric series, but we encounter a problem with the direct comparison test. The problem is it might be difficult to determine that term-by-term comparison that is necessary. We can't justify the preamble of the direct comparison test, in other words. So when this happens, we're going to use the limit comparison test, or I'll abbreviate that as LCT. So here's your limit comparison test. First, let's look at the preamble. A sub n greater than or equal to 0 and B sub n greater than or equal to 0. So we're still dealing with positive term series. The limit, we're going to create a limit here. The limit as n goes to infinity of A sub n over B sub n. And we're going to call that limit L. If that limit L is between 0 and infinity, in other words, if L is finite and positive, then the series A sub n and the series B sub n, they both converge or they both diverge. If L happens to equal 0 and the series B sub n converges, then the series A sub n converges. If L happens to be infinity and the series B sub n diverges, then the series A sub n diverges. So that handles almost all the cases you can encounter. Let me just say that I think most of the time, if not all the time, you're going to end up with L being a finite positive number. But I wanted to put those last 2 lines in for completeness sake. So my personal notes for many years ago was that the limit comparison test is really good for comparing a, quote, messy algebraic series with a p-series. And we'll start to define what messy really means in an example. When I'm determining the p-series for comparison, what I'm going to do is I'm going to disregard all but the highest powers of n in both the numerator and denominator. And see, the series that I'm going to be using in the limit comparison test, the one I'm coming up with for comparison's sake, that's going to be the B sub n that was in the limit comparison test theorem. So to show you how this works, I think we should do an example. I have 3 parts to this example. As part A, that's starting to look a little bit like messy algebra. But you know what the drill is. I'd like you to write these 3 down, get them written down in your notes, because I'm going to head off to the chalkboard and work them out. All right, now we've seen another comparison test. This was called a limit comparison test. And I said we were going to use it when we couldn't effectively use the direct comparison test. When doing a term-by-term comparison might be difficult, where the preamble for the direct comparison test may not be easy to establish. And I said it was good for, looking at, quote, messy, I call this messy algebraic looking series, and comparing it to a p-series. So my guidelines. To figure out what I'm going to compare this to, I am going to say, well, let's look at the series where you ignore everything in the numerator except the largest power. So that gives you n squared. Ignore everything in the denominator except the largest power, which gives you n to the fourth. Now that simplifies down to 1 over n squared, which, isn't that nice? It's P series. P is 2. So we know that it converges. So now to use the limit comparison test, if I mentioned this in the slide, you have to look at creating the limit as n goes to infinity, a sub n over b sub n. The series that you come up with to do the comparison to, that's what you want to make b sub n. Let me just kind of circle that here. That's the b sub n. So we have to find a limit. Limit as n goes to infinity. Let's see, a sub n is this mess. 3n squared plus n over n to the fourth plus square root n. And then that's all going to be divided by b sub n. So divided by 1 over n squared. Well, rather than saying divided by 1 over n squared, why don't I multiply it by the reciprocal? Kind of save a step. So rather than writing the division, I'm multiplying by the reciprocal. So now we have the limit as n goes to infinity, 3n to the fourth plus an n cubed over n to the fourth plus square root n. And you know how to find this limit. You're going to find this limit by dividing everything in the numerator by n to the fourth and dividing everything in the denominator by n to the fourth. And when you do that, let's see, you're going to get the limit as n goes to infinity. See, that's a 3 plus a 1 over n, a 1 plus, okay, so n to the 1/2 divided by n to the fourth, that would be n to the, negative 7/2. So that's 1 over n to the positive 7/2. So when I find this limit, the limit as n goes to infinity of 3 is 3. The limit as n goes to infinity of 1 over n is 0. The limit as n goes to infinity of 1, 1. The limit as n goes to infinity of 1 over n to the 7/2, 0. So this limit is 3. 3 is most definitely finite and positive. So our conclusion, and I ran out of room here, so I'll write the conclusion here. Series 3n squared plus n over n to the fourth plus square root n. It converges thanks to the limit comparison test with the known convergent p-series 1 over n squared. Alright, that was kind of fun. Alright, part B. So part B, you're asked to determine if the series n equals 1 to infinity, 1 over the square root of n squared, if that beastie, if it converges or diverges. Let's see what this kind of looks like. To me, it kind of looks like the series 1 over, so I ignore everything in the denominator except the largest power. So that's the square root of n squared, which is the harmonic series, 1 over n. Now what do we know about the harmonic series? We know that series diverges. So in any event, this is what the b sub n is. I'm gonna use this version though, because there's a radical in here. So when I look at the power of the limit comparison test, so a sub n, 1 over the square root of n squared plus 19n. and that's divided by b sub n. So this is divided by 1 over square root of n squared. So instead of writing divided by 1 over the square root of n squared, I'm going to turn that into multiplying by the reciprocal. So that allows me to, well, just kind of multiply those fractions together. And now I can use a property of radicals. I have a square root over a square root, so I can just make one big square root with the fraction underneath it. Then, just kind of playing around, having some fun here, simplifying. I would come in under the radical, and similar to what we did here, under the radical, I'm going to divide everything in the numerator by n squared and everything in the denominator by n squared. So that will give me, well, n squared divided by n squared is 1. N squared divided by n squared is 1. 19n divided by n squared, well, that's 19 over n. I should be able to do the limit now as n goes to infinity. So the limit as n goes to infinity of 1 is 1. The limit as n goes to infinity of 1 is 1. The limit as n goes to infinity of 19 over n is 0. So I have 1 over 1 plus 0. That's 1 over 1, which is 1. The square root of 1 is 1, which is most definitely finite and positive. So that tells me that my series 1 over the square root of n squared plus 19n diverges thanks to the limit comparison test with the known divergent harmonic series. See, I told you it was going to be important to know something about the harmonic series, to know it by name and to know when it diverges. There was a part C. I didn't think I'd have enough room to put all three parts up here all at once, so let me erase this and get part C written up on the board. And let's see what we can come up with there. So part C was the series 1 over n times n squared plus 1. Which, keep in mind, this is 1 over n cubed plus n. Well, if that's 1 over n cubed plus n, I think I'm going to say, let's compare it to 1 over n cubed. Seems reasonable. We know this series. We know it's a p series. P is 3, which is greater than 1, so it converges. So here we go. Making our limit. Limit as n goes to infinity. A sub n over b sub n. And hopefully by now, in the two examples that you've seen, you know I'm going to use that series as the b sub n. So what do we have? We have the limit as n goes to infinity of a sub n, 1 over n cubed plus n. I decided to write it as, I decided to multiply that out, divided by b sub n. So divided by 1 over n cubed. So I'm going to write that as multiplying by the reciprocal. So we have the limit as n heads off to infinity, n cubed over n cubed plus n. And you know I'm going to come in here and I'm going to divide everything in the numerator by n cubed. I'm going to divide everything in the denominator by n cubed to get the limit as n goes to infinity of 1 over 1 plus 1 over n squared. That limit is 1, which is definitely finite and positive. So our conclusion the series 1 over n times n squared plus 1. It converges thanks to the limit comparison test with the known convergent p-series 1 over n cubed. Okay, there were a couple problems that I wanted you to do. Let's see. Right now I'd like you to do number 11 and 24. So you know the drill. You're going to pause the video, go to the homework, do number 11, do number 24. Once you're done, restart the video and I'll be here working them out. Alright, number 11, you were asked if the series n equals 1 to infinity, n squared minus 1 over n cubed plus 4, if that series converges or diverges. And I would say, well, kind of to me, it looks like the series n squared over n cubed, which is, simplifies to 1 over n, the harmonic series, which we know the harmonic series diverges. So why don't we crank it through the limit comparison test. We have the limit as n goes to infinity. Alright, so here's a sub n squared minus 1 over n cubed plus 4, divided by b sub n. That's b sub n. So you know I'm going to rewrite it as multiplying by the reciprocal. So we have the limit as n goes to infinity, n cubed minus n over n cubed plus 4. Divide everything in the numerator and everything in the denominator by n cubed. So we have the limit as n goes to infinity of 1 minus 1 over n squared. All that over 1 plus a 4 over n cubed. So the limit as n goes to infinity of 1 is 1. The limit as n goes to infinity 1 over n squared is 0. Limit as n goes to infinity of 1 is 1. And the limit as n goes to infinity of 4 over n cubed is 0. So 1 minus 0 over 1 plus 0, that is 1. It's finite, it's positive. Our conclusion, the series n squared minus 1 over n cubed plus 4 diverges thanks to the limit comparison test with the known divergent harmonic series. Alright, pretty cool. Pretty cool. So let's look at 24. Here you have the series n equals 1 to infinity. 1 over 3 to the n minus 2 to the n. I think here it's a little different. I'm going to compare it to the 1 over 3 to the n. When I look at the two terms in the denominator, 3 to the n and 2 to the n, yeah, they're both exponential functions, but the 3 to the n is overpowering the 2 to the n. It's increasing more rapidly than the 2 to the n, so that's why I'm ignoring it and going with the 1 over 3 to the n. You know 1 over 3 to the n is the same thing as 1/3 to the n. Means this is a geometric series. R is 1/3, which is less than 1. So we know that beastie converges. So let's look at our limit comparison test. The limit as n goes to infinity. A sub n over b sub n. That's the limit as n goes to infinity. A sub n over b sub n. Well, this is b sub n. So this is over 1 over 3 to the n. So you know I'm going to rewrite it as multiplying by the reciprocal. Then I just multiply those fractions together, and I have a 3 to the n over a 3 to the n minus 2 to the n. All right, folks, so here's what we have to do now. I would divide everything in the numerator by 3 to the n, and I would divide everything in the denominator by 3 to the n. Look what that gives us. It gives us the limit as n goes to infinity of 1 over 1 minus, now keep in mind that's going to be a 2 to the n over 3 to the n. So 2 to the n over 3 to the n, I can write that as 2/3 to the n. Limit as n goes to infinity of 1 is 1. The limit as n goes to infinity of 1 is 1. The limit as n goes to infinity of 2/3 to the n. Well, that limit is 0 because it's like an exponential decay. So that's an old limit that we learned way back in Calculus 1. So 1 over 1 minus 0, that's 1, which, as always, that's finite, and that's positive. So that tells me that my original series converges thanks to using the limit comparison test, and we compared it to the known convergent geometric series 1 over 3 to the n. Alright, those are kind of fun. In fact, they're so much fun, I have 3 more I'd like you to do. I would like you to, in the book, same section, do numbers 41, 47, and 49. So you know the drill. Pause the video, do those 3. When you're done, restart the video, and I'll be here at the chalkboard working through the solution. All right, what I kind of like about this block of exercises is you're starting to get a lot more tests under your belt. I think you're up to about 7 tests now. So the book's starting to put a block of exercises where the directions are, use whatever test you want, which goes back to the very beginning of our study of series. I told you recognition was going to be key and how to attack these infinite series. So in number 41, the sum n equals 1 to infinity of 1 plus 2 over n to the n power. What jumps out at me immediately is that the limit as n goes to infinity of 1 plus 2 over n to the n power is e squared. And that is not 0. So my conclusion, the series diverges thanks to the nth term test. That was a very quick one. And number 47, the series n equals 1 to infinity of 1 over square root of n cubed minus n plus 1. Okay, when I look at that, I'm thinking, maybe if I ignore everything under the radical except the largest exponent, well, what do we know? We have a p-series. This is a p-series. P is 3 halves, which is more than 1. So it converges. So this is a good candidate for the limit comparison test. Kind of some messy looking algebra. So limit comparison test. Limit as n goes to infinity. A sub n over b sub n. That's the limit as n goes to infinity. A sub n and then over b sub n. So instead of writing divided by 1 over square root of n cubed, you know I'm going to write it as the reciprocal multiplying by the reciprocal. And, well, we multiply the fractions together then, and we get the square root of n cubed over the square root of n cubed minus n plus 1. That old property of radicals. I can rewrite the square root over a square root as one big square root of the fraction. And we're starting to see these techniques often now. You know what I'm going to do now? I'm going to come in here and I'm going to divide everything in the numerator and everything in the denominator by n cubed to get 1 over 1 minus 1 over n squared plus a 1 over n cubed. So then the limit as n goes to infinity, that's 1, that's 1, that's 0, that's 0. So I'd have the square root of 1, which is 1, which is most definitely finite and positive. So our conclusion, the series 1 over the square root of n cubed minus n plus 1 converges thanks to the limit comparison test with the convergent p series square root of n cubed. So let's see. Oh, there was one more I wanted you to do. That was number 49. So I didn't think I'd have room, so let me grab my eraser. And let me put number 49 up here. 49 is kind of a cool one. It's subtle. It's got some coolness because of its subtlety. So let's see. 49 is the series n equals 1 to infinity of 1 over n plus 2 to the negative n, which, you know, I see this as also being the series n equals 1 to infinity of 1 over n plus 1 over 2 to the n. All right, here's what I think is cool about this. Here's what I think is kind of subtle about this. You know, look at this. Let me write it down. 1 over n plus 1 over 2 to the n. I know 1 over n plus 1 over 2 to the n. I know that is most definitely larger than 1 over n. I mean, these are the same. So over here I'm just adding a little bit more to it. So of course the sum would be larger than that. Well, what does that mean? Write down the preamble of the direct comparison test. There's the preamble of the direct comparison test. We know the series, just make a place-by-place comparison here, direct comparison test. We know 1 over n diverges. It's the harmonic series. So we know this series, 1 over n plus 1 over 2 to the n, diverges thanks to the direct comparison test with the known divergent harmonic series. That was a cool one. I really liked it. Alright folks, so that's it for this section. So what you can do now, head off and do the exercises in this section. Thanks for watching.